As a manager, you should be comfortable with evaluating capital projects, anywhere from replacing a copier to Amazon relocating or creating an additional headquarters. The other thing you want to be comfortable with is the time value of money, because that concept is part of several of the tools used to evaluate capital investments or capital projects. So as we go through this solution walkthrough for problem 12.1b, I will use this also as an opportunity to reinforce some of those concepts. I strongly recommend that you utilize the Appendix A of your textbook for a quick summary of some of these key concepts regarding the time value of money. In this problem, there are 3 projects that are being evaluated, and we're assuming that they are mutually exclusive projects, which means if we accept one, we would not be able to accept the others. However, given the nature of the projects, it would not really matter. The project itself, each project has a time horizon of 5 years, and the company is requiring a return on its investment of 12%. This rate could have been determined based on what it would cost to borrow from the capital market, maybe to issue shares or to issue bonds. But in any case, the company is requiring a return of 12%, and each project has 5 years. We are told what the initial investment is for each project. Project Mary, $140,000 is the initial investment. Project Winnie, $175,000, and Project Sarah, $190,000. We're also given the net income, the annual net income for each project. And here is a critical point. Net income is not the same as cash flow. And when we are evaluating capital projects, we do want to focus on cash inflow and cash outflow. So this is net income, which of course you may recall is simply revenue minus expenses using the accrual method. But we will want to know what is the annual cash flow for each of these projects. So let's start with what we are being asked to do. We are asked to compute the cash payback period for each project. In other words, how long will it take for each project to return the initial investment required for that particular project? And so we start with Project Mary. The initial investment is $140,000. And we want to find out how long it will take us to recoup the $140,000. Again, the first thing we have to do is convert the net income into cash flow. And so what we do in this case is that we will add back the non-cash expense that was used to derive the net income. And so to find out the depreciation, which is the only non-cash item in this case, we take the initial investment of $140,000 and we subtract the salvage value, which in this case is 0. So $140,000 minus the salvage value of 0 will give us, and then divide that by 5 will give us $28,000 per year. And so the depreciation, which is straight line, will be the same amount every year. So $10,000, which is the profit each year. The profit is the same each year for Project Mary. And so the annual cash flow will be the same, which is the $10,000 net income, add back the depreciation. So the annual cash flow would be $38,000. And so how long will it take us to get back $140,000? We would simply divide 38,000 into 140,000, since it's the same amount every year, and it would take us roughly 3.68 years to recoup 140,000. Alternatively, you could keep adding 38,000 until you get to 140,000, which is the concept or the approach that we will use for projects where the annual cash flow is dissimilar. So let's move on to the second project, which is Project Winnie. This one requires an initial investment of $175,000, but notice in this case that the net income differs. It gets smaller each year. And so again, we will have to convert the net income to cash flow. So we take the initial investment of $175,000, and it's going to be depreciated over 5 years because that's the duration of the project. There is no salvage value, so under straight line it would be 175,000 minus 0 divided by 5. And when we do that, we get our annual depreciation for Project Winnie of $35,000. And so the annual cash flow will be the net income for year 1 plus the depreciation, and we get $47,500. For year 2, we would do a similar calculation, 12,000 plus the add back the depreciation, we get 47,000. Third, fourth, and fifth years, we do a similar approach, and you see the cash flows for each of those years. Cumulatively, we will then determine what the amount would be. So we take the first year, add it to the previous year, which is 0, and the cumulative would be 47,500. Then we add 47,500 to 47, we get 94. We add 94 to 46, we get 140,500. And we add that to 43, we get 183,500. And then we add finally to 41,000, we end up with 224,500. So over the life of this project, Project Winnie, a total of $224,500 will be coming in. Again, this is not accounting for the time value of money. It is simply assuming that $47,500 received in year 1 is no different from $41,000 received in year 5. Therein lies one of the major deficiencies of the simple payback period. However, finishing the problem, we take the initial investment of $175,000, and you will notice based on the cumulative cash flows, by the time we get to year 3, we're at $140,500, and in year 4 we exceed the $175,000. So we know it's going to take no more than 4 years. So it will be 3 years, plus we need an additional $34,500 to get us to $175,000. And so the amount available in the 4th year is $43,000. And so we divide the amount needed by the amount available, and we will need 80% of that amount in year 4. So the payback then will be 3 years plus 0.8 or 0.80 of the 4th year. So the total will be 3.80 years. 3.80 years is the payback. So Project Winnie will take a little longer than Project Mary, 3.68 versus 3.8. And of course, we would want to get our money back as quickly as possible, and so the shorter the payback period, the better. Again, the simple payback does not account for the time value of money. There is a modified or a discounted payback which would have found the present value for each of these annual cash flows and then use those values to determine the payback period, which is an improved version of the payback. Let's move on to the third project, and this is Project Sarah. Again, because the annual cash flow is different for each year, we will have to calculate the annual cash flow separately. And so we take the initial investment for this third project, Project Sarah, and it's straight line depreciation. So we take the initial value of 190 minus the salvage value of 0, divide by the useful life of 5 years, and that works out to $38,000 per year. So we take the net income for year 1, add back the depreciation that was taken out for that year, and the cash flow is now $57,000. We do a similar calculation for year 2. We take the net income for that year, which is given, and we add back the depreciation of $38,000. That brings us to $54,000. And again, we do that for each of the remaining years. Year 3, we get 52. Year 4, we get 47. And year 5, we get $46,000. Cumulatively, we're just adding the amounts for each year. And so you will notice that by the time we get to year 3, we are at $163,000. Year 4, we have exceeded the 190. So we know we're not going to need more than 4 years to get our money back, to recoup our $190,000 that we invested. And so for your calculation, what you would do is you would take the investment of 190, the cumulative amount up to but not exceeding what we need. So we, after 3 years, we would have recouped 163,000. We need an additional 27,000 to get us to 190, and the amount available in that year is 47,000. And so 27,000 is 57% of 47,000, which is 27 divided by 57,000. And so we get 3 years plus 0.57 years. Therefore, the payback period is 3.57 years. Turns out that in terms of payback, Project Sarah has the shortest payback period, 3.57 years. We now move to another tool. This one is called the net present value, where you are accounting for the time value of money. For the net present value, we're taking the present value of the initial investment, how much money we're putting into the project, and we are finding the difference between that amount and the cash inflow that would be realized over the life of the project. And so for Project Mary, again, we are told that the project will be for 5 years, and we computed the annual cash flow to be $38,000. Recall that from our initial calculations, the annual amount is 38. And so what we're wanting to know is, if we're getting $38,000 every year for 5 years, and the required return is 12%, what is that worth today? Think of this like the lottery, where you are going to be receiving $38,000 every year for the next 5 years, and you are wanting to get the cash option, so you get the money today. And assuming that the rate of investment is 12, how much money would you get today if you wanted the lump sum? So that's the idea behind the present value of what we would call an annuity. If you're using the tables as is suggested by the template, then you would go to table 4, which is on page A10, and you look for n is equal to 5 years, and the discount rate or the required rate of return is 12%. So when you look in that column, you will see this factor. The 3.60478 is the value today of $1 invested every year for 5 years at a rate of 12%. So if this is what $1 is worth, Then if we multiply it by $38,000, we will get the present value of that annuity, which is $136,682. When we compare that with the initial investment of $140,000, we notice that the difference is negative. In other words, we would spend $140,000 today on this project, and over the next 5 years we would bring in the equivalent of $136,982, and so the net present value is a negative. And whenever you're doing project evaluations and your NPV is negative, that project should be rejected. So as of now, this project does not meet the acceptance requirements and it would need to be rejected. If you are using your calculator, which is a lot faster than using the tables, then you would make sure you have the time value of money function, and n would be 5. The interest rate would be 12%. The payment would be $38,000, and then you would compute the present value. Again, consult your user manual for your calculator, or follow the Appendix A in your textbook to see how the specific requirements for your calculator or some calculators would be utilized. So again, based on the tables, we would get our value, a negative net present value of $3,018. We follow the same procedure for the remaining 2 projects. Now for Project Winnie and Project Sarah, we have to do a slightly different approach, because unlike the first project where the annual cash flow was the same, in this case the annual amounts are different. So we have to find the present value for each year's cash flow and then add. So you would go to table 4, page A8. Notice over here we were using, I'm sorry, this should be table 3. This is table 3, not table 4. So we would go to table 3 on page A8, and you're looking for the present value of $1, whereas in table 4 it was the present value of an annuity. So present value, you look for n is equal to 1 and the interest rate of 12, and you will see this present value factor of 0.89286. This is telling me that $1 1 year from now is worth 0.89 cents today if it's invested at 12%. Think of it this way: if you took 89 cents today and invested it at 12% for 1 year, at the end of the 1 year you would have $1. Similarly, 2 years from now, if you were promised $1 2 years from now and the interest rate is 12%, then it would be equivalent to 79 or 0.79719 cents today. Again, if you were to take this amount and invest it for 2 years at 12%, then in 2 years you would have $1. We follow the same procedure for years 3, 4, and 5. You look for n is equal to 3 and the interest rate of 12. You will see this present value interest factor. 4 years, n is equal to 4, interest rate of 12, n is equal to 5, interest rate of 12, and we have our discount factors. So now we take each discount factor and multiply by the corresponding cash flow. So the cash flow for year 1 was $47,500. Recall from our previous work that that is the case. And so we would take the amount for that particular project, which is $47,500, and we multiply by the factor. So 47.5 times the PV factor, we get the present value of 42,411. We do the same thing for the second year. 47,000 is the cash flow multiplied by the discount, the present value interest factor. We get our present value. And I do the same thing for each. Again, the annual cash flow multiplied by the present value interest factor, I get the present value. Then we will add all of those values and we get a total of 163,213. So the value today of all of these cash inflows over the next 5 years is 163,213. And I compare that with the amount that I'm going to be investing today, 175,000, and you see that will come up short by 11,787. In other words, we have a negative net present value. So this project is actually worse than the first one because we had a negative NPV of 3,000 versus a negative NPV of almost 12,000. Again, both projects are unacceptable based on the NPV. Whenever it's negative, it's a thumbs down. But comparatively speaking, we would say that this is worse because it's a larger negative. Then we have the third and final project. Again, the same calculation. You take the annual cash flow, divide by the present value interest factor, and you get the present value. So I did that for each of these, and then add, and the total present value is 186,925. Compare that with how much we would have to spend today to acquire that project or invest in that project, and you can see that we would have a negative net present value of 3,075. All three projects have one thing in common when it comes to the NPV, and that is they are unacceptable. But if you were to rank them from the least unacceptable to the most unacceptable, then the one with the smallest or lowest NPV would be ranked first, and the one with the largest negative would be ranked third. The last tool is to compute our annual rate of return on each project. This is more of an accounting tool as opposed to a financial tool, but it could be part of your arsenal as you are evaluating your projects. I certainly wouldn't make a decision based on the annual rate of return, but certainly used it as a supporting argument for a project that I am recommending. How do I do this one? For each project, you will need to know the average net income, which is to take the total amount of income over the life of the project and divide by the number of years. So you recall that for the first project, we are told that the annual income is 10,000, so that gives us a total of 50,000. If you take the 50,000 and divide by 5, that turns out to be an average of 10,000 per year. We do the same thing for the remaining two projects. For Project Winnie, we take its total net income over the life, which is 49.5, divide that by 5, and you take for Project Sarah its total of 66,000, divide that by 5, and you get your average. And so you will see here that we have 10,000 for Project Mary, 9,900 for Project Winnie, and 13,200 for Project Sarah. Next thing is the original investment plus any salvage value. The salvage value, as you may recall, is 0 for each of these projects, and then we divide by 2 to get the average. And so in this case, 140 plus 0 divided by 2 would be 70. And then we would take the 10,000, which is the average net income, and divide by the average investment value of 70,000, and we would get a return, an annual rate of return of 14.29%. think about how these calculations can be manipulated. For example, if I'm a manager and I want to improve or boost my average rate of return, I could delay when a particular investment is being made so that my average investment is lower. But let's complete this project. We have for project Winnie, same calculation. We take the average net income, we take the original investment plus the salvage value of 0 divided by 2. We get an average investment of 87.5. Average net income divided by average investment gives us an annual rate of return of 11.31. And then for project Sarah, we take the average net income divide by the average investment of 95,000, and that gives us 13.89. If we were to rank these, the higher the percentage, the better. So Project Mary would be number 1, Project Sarah would be number 2, and Project Winnie would be number 3. Again, none of these projects should really be recommended given the fact that the NPV is negative. However, to complete the requirements of this problem, you will notice that Project Sarah is ranked 1 because it has the shortest payback period. For the present value, we have Project Sarah also being ranked number 1. It has the smallest negative, so it's the least unacceptable. And for the rate of return, the annual rate of return, Project Mary would be ranked 1. Again, if I were being asked to select from these 3 projects, none of them would be selected because the net present value is negative, meaning that each one of these projects, if we had accepted it, would actually decrease the cash of the company, and so it would be unacceptable.